In this podcast episode, Neil deGrasse Tyson, Chuck Nice, and guest Katherine Freese engage in an in-depth conversation about some of the most compelling topics in cosmology and particle physics. The discussion touches on the nature and detection of dark matter, the mysteries surrounding dark energy, early cosmic structures, including the intriguing concept of dark stars, and the implications of recent findings from the James Webb Space Telescope. The dialogue spans from theoretical considerations to cutting-edge experiments and observations aimed at unraveling the cosmos's darkest secrets. Katherine Freese explains that scientists are actively searching for dark matter particles through three main approaches: making them, shaking them, and breaking them. Making refers to particle accelerators, like CERN's Large Hadron Collider, where high-energy proton collisions might produce dark matter candidates such as WIMPs, weakly interacting massive particles. Scientists look for missing energy signatures indicative of particles that fly out of detectors unnoticed. Shaking involves direct detection experiments that attempt to observe the rare interaction between dark matter particles passing through Earth and atomic nuclei within ultra-sensitive detectors, often placed deep underground to shield from cosmic rays. Xenon-based detectors are currently favored because of their known detector technology, though they have become expensive due to high global demand. Finally, breaking points to indirect detection, where scientists look for signals arising from dark matter particle annihilations, such as neutrinos. Experiments like IceCube at the South Pole look for such neutrinos generated by dark matter interactions. A novel approach presented by Freese involves Paleo detectors, which replace volume with time by examining ancient minerals, specifically certain olivine crystals preserved in meteorites that have been accumulating particle interaction tracks for 1 billion years. Unlike current detectors that look for immediate collision events, Paleo detectors look for accumulated damage in geological samples deep underground, where cosmic ray interference is minimal. These detectors can potentially detect both dark matter interactions and neutrinos, revealing information about supernova rates as well. While still in experimental development, Paleo detectors represent a promising complementary method to existing dark matter searches. Freese discusses her theoretical work on dark stars, hypothetical first-generation stars composed mostly of normal matter but powered not by nuclear fusion but by dark matter annihilation inside them. These stars would be cool and massive, growing exceptionally large, potentially up to 1 million times the mass of the Sun, because their cool surfaces would allow constant accretion of ordinary matter without blowing it away, as typical fusion-powered stars do. Some of the very bright, early universe objects recently observed by the James Webb Space Telescope could be candidates for such dark stars. These objects might help explain the formation of early supermassive black holes and other enigmatic early cosmic structures described as blue monsters or red dots. When asked whether dark matter could form its own galaxies, Freese confirms that in the early universe, large protogalactic structures composed primarily of dark matter formed first, serving as the gravitational scaffolding into which ordinary matter later fell to form visible galaxies. There is also the possibility of purely dark matter galaxies with no stars, which would be invisible to conventional telescopes since dark matter does not emit or absorb light. However, such dark galaxies can be indirectly detected through gravitational lensing, where their mass bends the light of more distant objects. These invisible structures present opportunities for future discovery and have exciting implications for understanding galaxy formation. Discussing dark energy, the mysterious force driving the accelerated expansion of the universe, the podcast highlights uncertainties that remain despite extensive observations, including some conflicting results between different measurements of the universe's age and expansion history. According to Freese, current data mostly favors a cosmological constant, a form of dark energy that remains constant over time, consistent with Einstein's original general relativity formulation. Although some recent experiments, like DESI, Dark Energy Spectroscopic Instrument, have hinted at possible time variation in dark energy and a slowing acceleration, alternative and simpler analyses find these results inconclusive. Dark energy does not behave like matter despite contributing mass energy to spacetime. Instead, It causes repulsion and expansion rather than attraction or clumping. The enormous discrepancy, 120 orders of magnitude, between theoretical predictions of vacuum energy and observed dark energy density underscores it as one of the deepest unsolved problems in physics. In exploring possibilities beyond the cosmological constant, Freese touches on theoretical ideas involving extensions of Einstein's equations. One such concept involves extra spatial dimensions posited by string theory, where our familiar universe is a three-dimensional brane embedded within a higher dimensional bulk. Interactions or influences from other branes or the bulk might induce modifications to the universe's expansion equations, potentially accounting for observed accelerated expansion without needing a separate dark energy component. This idea, humorously dubbed Kardashian cosmology, plays on the notion of warped extra dimensions influencing cosmic evolution and suggests alternative frameworks to explain cosmological observations. The conversation also touches on neutrinos, another form of weakly interacting particles, and their detection via underground experiments and astrophysical observations. Neutrinos influence dark matter and cosmological studies since they also interact weakly and leave characteristic tracks in paleo detectors. Additionally, the Casimir effect is mentioned as a measured manifestation of vacuum energy in the laboratory, demonstrating that empty space is far from truly empty. Virtual particle-antiparticle pairs continuously pop in and out of existence, producing measurable forces on closely spaced plates. However, attempts to calculate vacuum energy theoretically yield values vastly too large compared to observed dark energy, creating a significant puzzle for theoretical physics. A question from the audience addresses how astronomers differentiate between redshift caused by galaxies' recessional velocities, Doppler shift from cosmic expansion, and redshift due to photons losing energy escaping gravitational fields, gravitational redshift. The hosts clarify that the dominant effect for distant galaxies' redshift is cosmological expansion stretching the light wavelength. While gravitational redshift occurs, especially when light passes through massive clusters, it is a secondary effect used to study those structures rather than the universe's overall expansion. The observed spectral line shifts confirm universal expansion rather than tired light or other alternative redshift explanations. Throughout the episode, humorous exchanges lighten the scientific discussion. The guests joke about Nobel Prizes, honorary titles, and celebrity-like nicknames for cosmologists and physicists. They recall historical figures such as Steven Weinberg, William of Occam's razor fame, and Edwin Hubble, connecting their fundamental contributions to contemporary astrophysics. The playful banter helps make the complex cosmic topics more approachable and engaging. Brief mention is made of the James Webb Space Telescope's unexpected discoveries of surprisingly bright and massive early galaxies, dating back to times where such objects were not anticipated under current models. These discoveries challenge assumptions about galaxy formation speed and processes and open avenues for explanations involving dark stars and altered early universe conditions influenced by dark matter and dark energy dynamics. The telescope's observations thus fuel ongoing discussions about cosmology's foundational questions. Freese summarizes the main candidate particles for dark matter under consideration. WIMPs remain favored for their weak interaction properties, allowing them to evade direct detection so far. Axions are another particle type that could convert into photons under magnetic fields, providing unique detection opportunities. Primordial black holes formed soon after the Big Bang may also contribute to dark matter, gaining renewed interest with gravitational wave detections of black hole mergers. Each candidate motivates different experimental and observational strategies, reflecting the multifaceted efforts to solve the dark matter puzzle. The episode underscores the ongoing collaborative quest in astrophysics and cosmology to understand the invisible majority of the universe's content. From underground detectors and space telescopes to new theoretical frameworks and ancient minerals, multiple lines of inquiry are pursued. The hosts encourage listeners to keep asking big questions, reminding that the universe is full of fascinating unknowns and that each breakthrough arises from persistent curiosity combined with rigorous scientific method.